So you've made it. We are at the end of our rope, at the end of our chapters, and you're probably wondering, why are we cramming in one more chapter? Well, there's a good reason. Polymers are huge. If you're a chemistry major, you'll be a chemist. You'll encounter polymer chemistry for sure in your career, and you may in fact work in the polymer industry. They apply to renewable energy in droves, solar photovoltaics, fuel cells, wind energy. They're all based on polymer chemistry. You are a polymer, it's true. Just about everything you do has something to do with an enzyme, which is a polymer in the form of a polypeptide. And they're just everywhere. So they're fascinating. They're in your life, in every aspect of your life, and the main reason Chapter 26 provides fabulous review. So we shall start with polystyrene, and let me just warn you that we're really just skimming the surface of Chapter 26. So use these mini lectures as a guide as to what is important. Although I will tell you that the American Chemical Society has said there should be more polymer chemistry in the chemistry curriculum, so there you go. Well, you know polystyrene. You've used it many times, your coffee cups or your igloos. Polystyrene is everywhere. And polystyrene is a good review of radical chemistry. It's an amazing reaction. You take this humongous vat of styrene, throw in a spoonful of some kind of radical initiator, add a little heat, and what do you get? You get polystyrene. So, what's going on here? Well, naturally, if we're going to take something as fragile as a peroxide and we're going to heat it up, we are going to homolytically cleave that oxygen-oxygen bond to give us two radicals in an initiation step. What is that radical initiator going to do? It's going to look around for something to react with, and of course there's tons and tons and tons of styrene around. So it will add to the double bond. And in so doing, what you get is, this will come as quite a surprise, just kidding, you get the most stable intermediate, in this case a radical intermediate, and naturally it is going to form on the benzoic carbon. So that's the first step in the mechanism. Now what? Well, now what means you just need to think like a molecule. Here's a radical. What else is around? What's it likely to react with? Well, remember that big old vat of styrene? What's it going to encounter? Another molecule of styrene. And so that radical is going to add to the double bond. That arrow looks pretty funky. Try that again. That radical is going to add to the double bond. Same as before. So now we've got this guy, and I'm going to put my phenyl group up. I am making a new carbon-carbon bond right there. I'm making the same old radical intermediate that I made before. And what do you think that's going to do? I'll give you a hint. It's going to find whatever is in the beaker or flask or vat. And so on and so on. And so eventually we have polystyrene, where there's many molecules of styrene that have added together. So N is a really big number, like tens of thousands, and that represents a unit that is used frequently in polymer chemistry. That's called the degree of polymerization. So what's interesting about polymers, this is an example called chain growth polymerization, and the important thing to try and keep in mind is that, you throw in that little bit of initiator, but there's many, many molecules of initiator, and they're all starting to grow a chain. So there's lots of polymer chains growing at once. And eventually, you'll have a mixture of several different polymer chains that somehow or other stop growing. It may be that your polymer chain will react with another polymer chain in a termination step. That's, that's possible. It's not favorable, but it's possible. That's just called combination. Or it is certainly possible that what can happen is called disproportionation. And in a disproportionation reaction, what happens is one radical abstracts a hydrogen from another radical. So we got the radical over here. And gives you a terminated polymer chain over here, because that radical gets quenched by the hydrogen. And this, of course, just gives you an alkene, where this is the rest of the polymer chain. So both of these possibilities end up in terminating the chain growth, and so you end up with a lot of different sizes of polymer chains in your mixture. So one of the big deals about polymers versus the kinds of molecules we focused on throughout the 14 weeks of OChem that we've survived, they're really, really big. They are humongous. When you think about lab, the kinds of molecules you've encountered have been, molecular weights maybe up to 300 or so. Polymers, humongous, tens of thousands of mass units. And as I've been trying to stress here, they're not homogeneous. I mean, when you get benzoic acid, you get a scoop of it out of a jar, it's benzoic acid. It's one molecule with one molecular weight. Not the same thing with polymers. You scoop out some polyethylene glycol and you're going to have a range of molecular weights. And as you can imagine, there's going to be some that have been formed, some chains that have undergone disproportionation, some that have undergone termination, and some that have been capped with different kinds of initiators or end groups. So the thing is, they're not one single molecule. The other really, really big deal about polymers is that their size really, really governs their bulk behavior. And it's still the same sorts of intermolecular forces we looked at in Chapter 1. Van der Waals, dipole, etc. But since they're so huge, that magnifies the extent of these intermolecular forces. Well, the nice thing is the patterns we've learned in OChem in terms of mechanism also apply for polymer chemistry. So, as we look at polymerizing ethylene or ethene, well, it's going to be the same mechanism. Addition to the double bond gives me that radical. That guy's going to react with another molecule of ethylene. And so it goes. So here is your repeat unit right there. And we could just write our polymer as N, where N is a really big number. So basically, polyethylene looks like this. Then, what about polyvinyl chloride? Well, we won't go through the mechanism. You can go through that on your own. but I think you'll be able to figure out that this guy should look like that. So polyvinyl chloride reacts in the same sort of radical chain growth polymerization mechanism. Good grief, not to give you that, to give you this. That's a chlorine. Alright, so the double bond is consumed, and you just have a long straight chain of hydrocarbon where every other carbon has a chlorine on it. So PVC pipes, that's what they look like. An interesting aspect of the physical properties of polymers can be seen in low-density polyethylene versus high-density polyethylene. And it's basically all a matter of cross-linking, and that's going to be beyond the scope of the course. But this is polyethylene, as we know. But under certain conditions, what can happen is one chain of polyethylene can cross-link with another. And that is depicted in this particular figure out of your textbook. So when you form a covalent bond between two polymer chains, you really improve the rigidity and structural robustness of your molecule, of your polymer. So low density polyethylene is used for things like, baggies, Ziploc bags, that sort of thing. And high density polyethylene is actually robust enough to be like plastic boxes and things like that. So there's a ton of polymer chemistry that we are not going to get to. There will be one more mini lecture on polymers because they're so cool, and it'll be more review of kind of the chemistry we've looked at in the latter part of this semester. So that's all for this one, and we'll see you in class.